Thank you very much, Professor Chenchi, for your kind introduction. And first of all, I would like to express my sincere thanks to the organizers and also the selection committee members for choosing me for this highly prestigious award. And it's my great pleasure and honor to be here. And the title of my talk today is Photocatalytic Water Splitting to Produce Green Hydrogen and Fuels on a Large Scale. Here I show the outline of my talk. After introduction, I will talk about the particulate photocatalysts using these two materials. And then I will move to the photocatalyst sheet and water splitting panel. After that, I'd like to introduce our recent attempts for the pilot-scale solar hydrogen production system. Then I will summarize and I a little bit discuss about the near future target. At first introduction, my main research subject is, of course, the most important one is the photocatalytic water splitting reaction. But we are also interested in catalytic surface reaction mechanisms by transmission and reflection absorption infrared spectroscopies. One of the key persons was Junko Nomura Kondo. She is now the professor of Tokyo Tech. We are also interested in the surface reaction dynamics by nonlinear thermal frequency generation spectroscopy using a pump probe method in a picosecond time regime. And we also interested in developing new materials for heterogeneous catalysis. Especially, we were interested in solid acid catalysts, such as carbon-based materials or proton exchange layered materials. We also developed the mesoporous materials of transition metal oxides, especially for applying to the photocatalytic reactions. And during the photocatalytic reaction, we occasionally found that mechanocatalytic water splitting reaction. Actually, this reaction was discovered by Professor Ikeda. He is now the Konan University's professor. And of course, today I will focus our attention on the photocatalytic water splitting reaction. But recently, my younger colleagues summarized that all of these subjects and published review articles last year in IACS catalysis. And my research career is shown here. I attended in 1972 University of Tokyo. Then I went on the School of Science and Department of Chemistry. At that time, my supervisor was late Professor Kenji Tamaru. And after I got the PhD degree, I immediately joined the Professor Onishi's groups as an assistant professor, that is at the Tokyo Institute of Technology, Chemical Resources Laboratory. There I spent 22 years. After that, I moved again to the University of Tokyo, in this case, School of Engineering. And in 2019, I became a university professor of the University of Tokyo. And a little bit earlier, I cross-appointed to Shinshu University. Now the name is Institute for Aqua Regeneration. So it is now in the middle of 2024. So at present, I have 2 labs in both universities. And especially in the University of Shinshu University, my colleague is Professor Satomi. And actually, I started my photocatalytic water splitting research work in 1979. That means that I have been continuing research on photocatalytic water splitting for about 45 years. Okay, to split pure water into hydrogen and oxygen using solar energy, at present, the most practical way is to use a solar cell or photovoltaics and then electrolyzer. And actually, both of these technologies are already commercialized, so it is not possible to implement into the social. But the question is price of hydrogen. And on the other hand, at the laboratory level, there are 2 distinct directions. One is a photoelectrochemical water splitting reaction. In this case, relatively high efficiency is achieved at the laboratory levels. However, the scalability is a little bit difficult problem. On the other hand, photocatalytic water splitting reaction, or sometimes it's called artificial photosynthesis. In this field, there are many researchers actually participating and using various different types of materials. But today, I'll focus our attention on the inorganic or semi-conducting solid-state materials because my major is heterogeneous catalysis. Therefore, our target reaction is very simple. We like to split pure water into hydrogen and oxygen using solar energy on heterogeneous photocatalysts. Of course, the motivation is as follows. If hydrogen is produced from solar energy and pure water, It can be clean and sustainable energy carrier as well as chemical resource. However, from the viewpoint of technology, the situation seems to be more serious because the production of solar fuels on a large scale at a low cost in the near future. Here I show that several examples of the various kinds of particulate photocatalysts. This white particle is a UV light responsive photocatalyst, and these colored particles are visible light responsive photocatalysts. And today I'll focus on photocatalytic water splitting reaction in two different ways. That is one step or two step or so-called D-scheme water splitting reaction. Then after that, I'll move to the photocatalyst sheet and water splitting panel. At first, let me get started from this one-step overall water splitting reaction. In this case, we use only one type of photocatalyst, and both hydrogen and oxygen evolution takes place on the same particle. So this is the simplest way to split water into hydrogen and oxygen. Oh, sorry. However, probably this is the most difficult way to split water. Here I show the simplified basic principles of one-step overall water splitting reaction. This is the normal hydrogen electrodes at pH equals 0. Therefore, of course, the hydrogen evolution potential located at 0 volt, and some dynamic oxygen evolution potential located at plus 1.23 volt. This is the band gap position of a particulate photocatalyst referring to this axis. Under photoirradiation, electrons in the valence band are excited into conduction band. Then conduction band minimum located more negative than this hydrogen evolution potential. These photo-excited electrons are thermodynamically possible to reduce protons into hydrogen molecules. But as far as we use N-type semiconducting materials, in almost all cases, we have to introduce a co-catalyst for hydrogen evolution, as shown here, to facilitate the electron transfer to proton and to generate hydrogen molecules. On the other hand, the valence band maximum located more positive than this oxygen evolution potential. Again, these photo-excited holes are possible to oxidize water molecules or hydroxide anions into O2 molecules. In this case, I didn't show any co-catalyst. Actually, in many oxide-type photocatalysts, the surface of the photocatalyst itself works as an O2 evolution site. But if we like to reduce the band gap energy, or if we like to use some non-oxide type photocatalyst, again, the introduction of the co-catalyst of for O2 evolution is useful. Today, I will discuss on both cases. Now, let me move to the next part, particulate photocatalyst. At first, a UV light responsive photocatalyst, especially I will focus our attention on aluminum-doped strontium titanate. Here, I show three photocatalysts which have been developed by our groups. This is a photocatalyst based on strontium titanate, which was developed when I was a PhD course student. This is one of the earliest photocatalysts which could evolve both hydrogen and oxygen in stoichiometric ratio. However, the quantum efficiency at this stage was very low. After I moved to the Tokyo Institute of Technology, we are interested in developing these kind of layered materials to split water, and the quantum efficiency was improved considerably, as shown here. But all of these type of photocatalysts are oxide-type photocatalysts, so these materials can use only UV light responsive photocatalyst. Actually, before 2000 years, the photocatalytic overall water splitting situation is as follows. Under UV light irradiation, many efficient oxide photocatalysts have been developed. Especially, I like to emphasize that the lanthanum-doped sodium tantalate modified by nickel oxide, this is a hydrogen evolution co-catalyst, and actually developed by Professor Kudo at Tokyo University of Science. Apparent quantum yield was more than 50% at 270 nanometers. At this stage, this is the highest efficiency for water splitting reaction. Now let me focus our attention on the strontium titanate photocatalyst. This strontium titanate is, as you know, that white colored powder and absorption edge located at about 380 nanometers. That means that these materials can use only a small portion on sunlight. However, the band gap position of these materials is suitable to evolve both hydrogen and oxygen. Therefore, these materials have a potential to be efficient UV light responsive water splitting photocatalyst. Here I show that our history of development of the strontium titanate-based photocatalyst. These works are actually carried out after 2,000 years. And in this case, at first, we just modified by rhodium and chromium mixed oxide for hydrogen evolution co-catalyst. I'll be back this co-catalyst later, but this co-catalyst is a very effective co-catalyst for hydrogen evolution. And we irradiated by xenon longer than 300 nanometers. When we used stoichiometric strontium titanate, the activity was almost nothing when we wrote in this scale bar, millimoles per hour. But actually, this photocatalyst also can evolve hydrogen and oxygen in 2-to-1 ratio. After that, we modified the property of the strontium titanate. Here, I focus on the aluminum-doped systems. And when we use the so-called flux method, at this stage, as you see here, the apparent quantum yield is already exceeded 50% at 365 nanometer. This is a very high quantum efficiency already at the wavelengths which is included in sunlight. After that, we added co-catalyst for O2 evolution in addition to this hydrogen evolution co-catalyst. At first, we found that when we use a molybdenum oxide, the apparent quantum yield was increased to almost 70%. But after some period, we realized that when we use a cobalt oxide, and then all the metallic component, metallic component of this co-catalyst, I mean the cobalt and the rhodium and chromium were photodeposited. Apparent quantum yield exceeded 90%. And this was actually developed by Professor Takata at Shinshu University. But this is extremely high quantum efficiency. So I like to discuss about this type of photocatalyst a little more in detail. Here I show the preparation procedure of this photocatalyst. After choosing strontium titanate, suitable strontium titanate, then we use a flux as a strontium chloride and alumina, that is the dopant. The ratio is 10:1 to 0.1. Then we calcine this mixture in air at 1423 Kelvin for 10 hours. Then we can get this kind of particles. The particle size is about a few hundred nanometers, and the amount of the aluminum dopant was about 0.1 atomic percent. Here I show the wavelength dependence of this apparent quantum yield of this photocatalyst, and this is the data that I shown in the previous slide at 365 nanometers. We also measured at different wavelengths, as shown here. In our case, this apparent quantum yield is defined based on the total photon number, which was introduced into our reactor. That means that some small portion of the introduced photons are scattered out without being absorbed by our photocatalyst. So we consider that if we could measure the so-called internal quantum yield, I mean that's based on the total photon number, which was really absorbed by our photocatalyst, at least in this region, we consider that internal quantum yield is already very close to 100%. So I would like to say that it is possible to split pure water into hydrogen and oxygen using a particulate photocatalyst with a quantum efficiency of almost unity. Now, let me introduce how to prepare this type of photocatalyst in more detail. As I said, we use a photodeposition method of all the metallic component of the co-catalyst in aqueous solution. At first, we construct the hydrogen evolution co-catalyst, that is rhodium and chromium core-shell structure. The first reaction is metallic rhodium nanoparticle deposition using a photoexcited electrons to reduce rhodium-3+. However, if this metallic rhodium nanoparticles is exposed to the surface, the reverse reaction from the product of hydrogen and oxygen to form water molecules proceeds. To prevent such a kind of reverse reaction, we coat this metallic rhodium nanoparticles by chromium oxide, hydroxide. In this case, again, we use a photoexcited electrons to reduce chromium-6+ into chromium-3+. By these two reactions, we can construct a core-shell structure. And in these two reactions, we use the photoexcited electrons. So these reactions are so-called photoreduction reaction. After that, we construct the oxygen evolution co-catalyst. That is a cobalt oxide. In this case, we use a photoexcited holes to oxidize cobalt-2+ into cobalt-3+. More precisely, cobalt oxide. So this reaction is a so-called photooxidation reaction. So during this modification, we examined what happened on our photocatalyst by using high-resolution STEM images. This is one particle of our photocatalyst, and sorry, this length is 100 nanometers. And then from this part, we obtain this kind of electron diffraction pattern. And from this electron diffraction pattern, we can identify that this flat facet and these flat facet are 100 facet and their family. And I hope that you can see very small particles that exist on these facets. And all of these particles are actually rhodium and chromium coaxial structure for hydrogen evolution. In addition to that, there are many different facets a little bit curved like these ones. In this case, we are not able to identify. But for simplicity here, let me say that this is 110 facet. And on this 110 facet, we observed only the oxygen evolution co-catalyst. That is the cobalt hydroxide. That means that from the very beginning stage, photoexcited electrons and holes are transported to different facets with almost 100% efficiency. Then the question is that, what is the driving force? We consider that there exists some internal electric field within this particle. However, we are not able to directly measure the internal electric field by experimental method. So we decided to carry out a simplified two-dimensional simulation to determine the internal electric field. This is our model structure. This is 100 facet, this is 110 facet, and this is x prime axis, this is y prime axis. Then we set the work function difference between these two facets to be 0.2 eV. This seems to be reasonable from the literature value. Then we carried out a simulation like this one. Along with the x prime axis, as you see here, the internal electric field is downward towards the 100 facet. This kind of internal electric field tends to accumulate photoexcited electrons on the surface of 100 facet. On the other hand, along with the y prime axis, the internal electric field is upward toward 110 facet. This kind of internal electric field tends to accumulate photoexcited holes on the surface of 110 facet. Actually, our model structure is this kind of two-dimensional structure. And this is a more quantitative analysis of this kind of accumulation. I don't get into detail of this evaluation, but from this kind of evaluation, we can conclude that almost the 100% efficiency of excited electrons and holes are possible. So we believe that this kind of internal electric field is a driving force to achieve almost 100% efficiency of overall water splitting reaction. Sorry, no, okay. Visible light responsive photocatalyst now move to the gallium nitride zinc oxide. And probably, as you know, that the gallium nitride zinc oxide, in both cases, they have an ultralight structure. However, interestingly, that the lattice mismatch of these two materials is only 0.8%. However, the band gap energy of these two materials are in both UV light region. Then, if we prepare the solid solution between these two materials, as you see here, that the absorption edge is extended into the visible light region. And the preparation procedure of these materials is somewhat interesting, which was developed by Professor Maeda. He is now the professor of Tokyo Tech. At first, we mix zinc oxide and gallium oxide in 2:1 ratio. Then we carried out the nitridation using ammonia at 850 degrees C. Then we obtain the gallium nitride zinc oxide solid solution. And this is a solid solution of gallium nitride zinc oxide of yellow color powder. The reason of this yellow color, the simplest explanation is that by forming this kind of a solid solution, we can make a new bonding between zinc and nitrogen, which can absorb visible light. Then this is a SEM image of this particulate photocatalyst. This is 1 micrometer scale bar. So the particle size is about a few hundred nanometers. Then this is a procedure to find a suitable co-catalyst for this solid solution photocatalyst. And here I showed many metals, but this is not the metal itself, but it's a metal oxide. And when we use nothing of no co-catalyst activity, there is no activity. On the other hand, when we use a nickel oxide or ruthenium oxide, we obtain considerably good activity for both hydrogen and oxygen evolution. But these two materials has been known that these are good co-catalysts for water splitting reaction. But the interesting one is this one. When we use a chromium oxide, no activity. That means that the chromium oxide itself does not have ability as a co-catalyst. However, when we mix this chromium oxide with all other these metallic oxide, we obtained much better activity as shown here. Okay, for example, if in the case of copper oxide, when we use only copper oxide, our activity was almost nothing. However, when we mixed with chromium oxide, as you see here, we could get considerably good activity for hydrogen and oxygen evolution. And among all of these combinations, the highest activity was obtained by rhodium and chromium mixed oxide, as shown here. Unfortunately, this is the element, the most expensive element. That is a problem for us. But anyway, this rhodium and chromium co-catalyst shows a very good activity for hydrogen evolution. And this is the result of such a kind of experiment using this rhodium and chromium mixed oxide as a co-catalyst, and only visible light irradiation. As you see here, both hydrogen and oxygen evolution takes place exactly in 2-to-1 ratio. And in this particular case, the quantum efficiency at 410 nanometers was about 5.2%. This is the first example of which succeeded in splitting water using visible light by one-step water splitting photocatalyst. Now, let me change to the tantalum-3N5 potassium tantalate photocatalyst. Actually, the absorption edge of this tantalum-3N5 is located at about 600 nanometers. And this material has a so-called anisobite structure, and the band gap energy is about 2.06 eV. Actually, we worked on this material for more than 20 years because that this material's band gap position is suitable to split water into hydrogen and oxygen. However, in the first 15 years, we had never succeeded splitting water. Actually, in that case, we used starting materials, this material, tantalum pentoxide. As far as we used tantalum pentoxide, we had never succeeded splitting water into hydrogen and oxygen. But occasionally, our purpose is a little different, but when we used potassium tantalate as a starting materials, and then we carried out nitridation at 850 degrees C for a very short period, we prepared tantalum-3N5 on potassium tantalate. I showed that such a kind of system by SEM image. Okay, this is the starting materials of potassium tantalate. This is a 500 nanometer scale bar. And after 0.25 hours nitridation, only 15 minutes nitridation, at the corner, you see that we observed some growing over nanorod. After 1 hour of nitridation, we clearly observed this kind of nanorod is formed. And this is a high-resolution STEM image, and here is potassium tantalate, and these are the nanorods, like this one. And this is more magnified structure. As you see here, this material is highly crystallized up to uppermost layers, like this one. And more importantly, what is? Okay, sorry. The lattice constant of this materials is exactly the same with tantalum-3N5. So we are now sure that we have prepared tantalum-3N5 nanorods on top of the potassium tantalate. Then we decided to use this tantalum-3N5 for water splitting photocatalyst. At first, we loaded metallic rhodium again for hydrogen evolution. But in this case, we used only visible light to excite only this tantalum-3N5 and to deposit metallic rhodium nanoparticles onto this tantalum-N5. This is STEM images, and this is a 2 nanometer scale bar, and as you see here, on this nanorod, we observe that 2 to 3 nanometers metallic nanorod. And this is a lower magnification. This part is potassium tantalate, and this part is nanorod. And as you see here, these small particles located only on the metallic TA3 nanorod. So this is a structure that we wanted to construct. Then we coat these metallic rhodium nanoparticles again, chromium oxide, or again that using visible light. Okay, this is the structure of our photocatalyst. In this case, we don't use any co-catalyst for autoevolution. And in distilled water without any electrolyte and under visible light irradiation, as you see here, both hydrogen and oxygen evolution takes place exactly in 2 to 1 ratio. But this system still have some problem. That is this one. The quantum is at 420 nanometers, still about 0.25%. So we still have a lot of room to improve this type of photocatalyst. Okay. Now, so far I discussed about several different types of photocatalysts for water splitting reaction. But our purpose is not only to develop such a kind of photocatalyst, but we like to apply this kind of photocatalyst to a wider area to produce green hydrogen on a large scale. To extend to such a wide area, there seem to be several different ways. But one of the most straightforward ways is to construct this kind of water splitting panel that is more or less similar to the photovoltaics panel. To construct this kind of water splitting panel, we need to fix our particulate photocatalyst in 2 dimensions. We call such a kind of system as a photocatalyst sheet. Now let me move to the next part, photocatalyst sheet and water splitting panel. At first, this scheme, water splitting photocatalyst sheet. I mean that I will discuss about this kind of 2-step water splitting reaction, so-called this scheme water splitting reaction. In this case, we use 2 different types of photocatalysts for hydrogen evolution and oxygen evolution. And these 2 photocatalysts are actually connected by so-called redox shuttle, or we connect some electron conducting layer. And actually, the first example is that we use the lanthanum rhodium co-doped strontium titanate for hydrogen evolution, and the molybdenum doped bismuth vanadate for oxygen evolution. But this combination is not really our original system, but it was reported by Professor Kudo at Tokyo University of Science. And they used these types of photocatalysts in a suspended system. And they used iron 2+, 3+ redox shuttles and electron to connect these 2 photocatalysts. And the quantum yield at 420 nanometers was about 4.2%. Okay. Then we tried to prepare our photocatalyst sheet. Here I show that the preparation procedure of our photocatalyst sheet. The preparation procedure is relatively simple. We mix these 2 types of powder photocatalysts in an isopropanol solution, then just drop casting on a glass plate, and then after drying isopropanol, we obtain this kind of mixed particle layer. The thickness is at most about 10 micrometers. Then after we deposit the gold or carbon as an electron conducting layer by evaporation or sputtering. Then after annealing at suitable temperature to fix this electron conducting layer to our photocatalyst, we put another glass plate on top of this one. But in this case, this glass plate has a double-sided carbon scotch tape here. Therefore, after pushing and peeling off, we can obtain this kind of structure. After removing the physically adsorbed particles with sonication, we can obtain this kind of photocatalyst sheet prepared on a glass plate. Then if we observe that this surface by SEM, okay, this is a top view of the SEM image. And as you see here, the structure is not really so well organized. This red dot indicates the oxygen evolution photocatalyst. This green dot indicates the hydrogen evolution photocatalyst. And in this particular case, we used a gold as an electron conducting layer. So the whole structure is like this one, not really well organized. But if we put this type of photocatalyst sheet, especially in this case, we use a carbon as an electron conducting layer in a distilled water, then irradiated by air mass 1.5G solar simulator, we obtain this kind of bubbles coming out. This is the bubbles of hydrogen and oxygen exactly in 2-to-1 ratio. And the quantum yield at 420 nanometers was more than 30%. It is much better than the suspended system. But we have a little bit concern about this type of photocatalyst sheet because the scalability or cost is a little bit expensive because we use a vacuum system to prepare this type of photocatalyst sheet. So more recently, we are now trying to prepare this scheme photocatalyst sheet by all wet processes. Here I show that one of such a kind of examples. In this case, for hydrogen evolution, we use a samarium titanium oxysulfide, and then platinum chromium coaxial structure is for hydrogen evolution, and this iridium oxide works for whole transfer co-catalyst. And for O2 evolution, again, bismuth vanadate, and cobalt oxide is for O2 evolution. And these 2 photocatalysts are connected by single-wall carbon nanotubes. And the preparation procedure is very simple. We just mix these 3 components in an aqueous solution by only stirring. Then we carry out just a filtration, which is a normal filtration system in a laboratory, chemistry laboratory. Then we obtain this kind of filter paper, which has a 3 components on the surface of this one. With this, we use this type of photocatalyst sheet directly. And then this is the SEM image of this surface. And these flat particles is actually the samarium titanium oxide sulfide for hydrogen evolution. And these small particles are bismuth vanadate for auto evolution. And these particles are connected by bundle of the single-wall carbon nanotubes. Okay, this is the structure of our photocatalyst sheet. Then we put this photocatalyst sheet, and then under visible light irradiation, as you see here, bubbles is coming out like this one. So we consider that we are now preparing the scalable method to prepare the Z-scheme photocatalyst sheet. And in addition to these combinations, we are also using, for example, tantalum 3N5 for auto evolution, or lanthanum titanium copper silver oxide sulfide for hydrogen evolution. We are now examining various kinds of combination of overall water splitting reaction. Now let me move to the next part, photocatalyst sheet and water splitting panel. And in this case, I like to discuss about one-step photocatalyst sheet. And this is the exactly same materials with this one, aluminum doped strontium titanate. In this case, the preparation procedure is very simple. At first, we prepare the active photocatalyst by modifying these co-catalysts, and then mix with nano-sized silica particles in an aqueous solution. And then we spray coating on a frosted glass plate, and then drying and calcined at 90 degrees at low temperature for several hours. And then this nano-sized silica works as glue to fix our active photocatalyst. This is a 500 milliliter beaker just filled with distilled water. And if we put this beaker outside under sunlight or irradiated by a solar simulator, you see that this kind of bubble is coming out. This is the bubbles of hydrogen and oxygen exactly in 2-to-1 ratio, which is produced by UV light included in sunlight. And this is a cross-sectional view of this photocatalyst sheet. This is 10 micrometer scale bar. As I said, we use a frosted glass plate like this one. And these white particles are our photocatalyst, and this dark gray part is a nano-sized silica. To observe this part in more detail, we measure the high-resolution STEM images. So this is a 10 nanometer scale bar. In this case, this black part is our photocatalyst. In between, there exists a nano-sized silica. The particle size was about 10 to 20 nanometers. In between, as you see here, there is a void, like these ones. And this void is actually filled with distilled water. And the evolved hydrogen and oxygen molecules dissolve into this distilled water under supersaturated condition. The reason that the bubble doesn't form is that the space of this void is too narrow. Therefore, that this kind of supersaturated condition continues up to the surface of this photocatalyst sheet, and there bubble is formed. And this is an optical microscope image. This is 1 millimeter scale bar, and as you see here, bubble is formed very limited places on this photocatalyst sheet at exactly the same place, like this one. Okay? This is a real feature of the bubble formation on this photocatalyst sheet. Then we use this photocatalyst sheet to construct a water splitting panel. In this case, the size was 25 centimeter times 25 centimeter, using 0.4 gram of photocatalyst, 0.9 gram of nano-sized silica. This is a side view. Here we have a photocatalyst sheet, and this is a gas outlet. Water inlet is here, but we introduce water very, very slowly. And the thickness of the water layer is only 100 micrometer, 0.1 millimeter. This is the real structure of our water splitting panel. In this particular case, we irradiate by UV LED at 365 nanometer. I hope that you can see that small bubbles going up quickly and then go outside through this gas outlet. And I should say that the rate of water splitting reaction in this case was exactly the same when we used a millimeter thickness or a centimeter thickness of water layer. That means that 100 micrometer thickness of distilled water is enough to be effectively split into hydrogen and oxygen. Then we use this water splitting panel to construct a pilot-scale solar hydrogen production system. Here I show that our design. These are our water splitting panels, and evolved hydrogen and oxygen mixture containing water vapor is carried to this gas separation unit, which has a gas separation membrane. And here we constructed 500 100 square meter prototype water splitting panel at Kakioka Research Facility of University of Tokyo. Here is a small hill, and on top of this, there is a flat places, and there we constructed this kind of system. And in this case, we use a 1600 water splitting panel with a size of 25 centimeter to cover 100 square meter. In addition to that, this is a gas separation unit. And this is the bubbles of hydrogen and oxygen evolving before introducing into our gas separation unit. This experiment was carried out September 30th in the beginning of fall, so that at this stage that we obtained about 3.7 liters per minute of hydrogen and oxygen evolution. Then we separate hydrogen from this mixture. We are developing several different types of membrane, but here I show that one of the simplest and easy way to separate hydrogen. And that is a commercially available polyimide hollow fiber membrane. This is possible to purchase from industry, but this cartridge is not designed for hydrogen separation. But this cartridge was designed for compressed air dehumidification. However, this membrane can also separate hydrogen from the mixture. The method is like this one. At first, we introduce 1 bar of hydrogen, oxygen, and water vapor mixture from here, then go through this one and go outside here. And this side is evacuated to up to about 0.1 bar. Therefore, the pressure difference between outside and inside of this hollow fiber membrane is less than 1 bar. So we don't need to use so much energy to separate hydrogen. And this is a photograph, and the length of this cartridge is 32 centimeters. And the inside of this membrane cartridge is filled with hollow fibers. The number is 2300, like this one. And the inner diameter of this hollow fiber is 0.3 millimeter. And using this cartridge, and we carried as a one-day experiment for separation of the hydrogen. This was carried out October 2nd in 2020, and this is almost a clear day. And then this is the accumulated amount of evolved hydrogen and oxygen. In this case, we obtained almost 100 liters of hydrogen and oxygen mixture. And this curve is a little bit complicated, busy one. But this blue curve is hydrogen-rich filtrated gases. In the morning and in the evening, the purity of hydrogen is more than 95%. However, in the daytime, the hydrogen purity was about 92 to 93%. This is due to the lower selectivity of this membrane at high temperatures. So that from these curves, we can obtain that hydrogen recovery in this particular case was about 73%. And as you know well, that explosion region of oxygen-hydrogen mixture is very wide. If we avoid this explosion region at hydrogen-rich side, we need to obtain the more than 95% purity. However, in this particular experiment, in the daytime, our mixture is still inside of this explosion region. But this experiment was carried out in 2020. So at present, we are now obtained continuously that more than 96, 98% purity. And by quenching contamination of oxygen, we can get more than 99.9% purity. And also that the hydrogen recovery is now being improved to 90%, but we like to achieve 95 to 98% of hydrogen recovery. Now let me summarize and discuss a little bit more about near future targets. Here I show our image of future implementation of this new technology into the real world. We like to make one unit to the 10,000 square meter, 1 hectare. And in this area, we have only one gas separation unit. And if we like to extend to 1 square kilometers, we just increase the unit number to 100. And at the very beginning stage, we like to achieve the SH value to 5%. This is the value that fits our collaborating industry people evaluated to commercialize this new technology. Here I show that the efficiencies of various photocatalytic water splitting reaction. This is the apparent quantum yield in a logarithmic scale, and this is this axis shows the absorption edge of our photocatalyst. This circle shows one step over water splitting photocatalyst. This triangle shows two-step water splitting systems. And these black ones actually is a little bit old photocatalyst. And more recently, for one-step overall water splitting reaction, we have developed these types of photocatalysts. And for this scheme water splitting reaction, we developed these types of photocatalysts. This is not only our group's works, but it includes Professor Kudo's groups and Professor Sakata's group of Yamaguchi University. But as you see here, STH value of 5% is here or upper part, and STH value 10% is around here. As you see, we have never succeeded in getting to this region. So actually, the theoretical limit, if we use a one-step overall water splitting reaction, is around here. Okay, if we use a barium strontium tantalum oxynitride, the theoretical limit is about 70%. If we use a barium strontium tantalum oxynitride, the theoretical limit can be about 20%. Actually, we consider, judging from the band gap energy, about 2 electron volts, we believe that we have enough driving force to improve the efficiency of water splitting reaction. So we are now focusing on some limited target to improve our efficiency to get into this region in a very near future. And another thing I'd like to discuss here is this one. Green hydrogen production is intermittent. Of course, at night, no production of hydrogen. So it is not so good idea to store the hydrogen at a high pressure on a large scale. So we like to store at a small scale at a constant volume. Then that's hydrogen we like to transform immediately to more easily storable and transportable materials such as MCH, methyl cyclohexane, or methane for green fuels, and ammonia for hydrogen carrier as well as green fuels. But to achieve this kind of reaction, we consider that DSS operation, daily start and stop operation, is better. To achieve such a kind of reaction, we need a catalyst which not a photocatalyst, but a thermal catalyst, which can active at 200 to 300 degrees C. And actually, in the case of MCH and methane, already such a practical catalyst does exist. And in the case of ammonia, this is a little bit challenging. And then here, let me at first discuss about the methane formation. And here I show that our structure, which we constructed for the European Innovation Council's Horizon Prize contest on fuel from the sun, artificial photosynthesis. In this case, here we have a water splitting panel, and this is a gas separation membrane. And after quenching our gas, we obtain the pure hydrogen, and it is mixed with carbon dioxide to form methane, which works at about 200 degrees C, like this one. A more detailed structure of this system was already reported in IACS engineering. And this is a real structure. The rule of this contest is that within a 5 meter times 5 meter scale area, all reaction has to be completed. Then that we have to produce green fuels except hydrogen. So we chose methane. And this is a water splitting panel. And here we have a hydrogen separation membrane. And this is a methanator. And this is a methane container bag. And actually, we carried out this kind of experiment in July 2022 at European Commission's Joint Research Center in Spura, Italy. And we carried out a 3 days DSS operation, all computer controlled. And then this system worked well. And I think that from this kind of experiment, we are rather confident that it is not so difficult to extend this type of system to the wide area, as far as we can develop a highly efficient water splitting panel. And at the last part, let me just discuss about ammonia formation by this method. And here I show that activity of ammonia formation per unit volume as a function of temperature at relatively mild reaction conditions. This catalyst is actually new catalyst was developed by Professor Hara at Tokyo Tech. And then this industrial catalyst is a comparison, that is a Haber-Bosch type catalyst. And Professor Fukuhara is an expert of the structure of the catalyst. And it is suitable for our purpose, and also it can avoid the pressure drop in a reactor. We are interested in this region, from the 200 to 300 temperatures, and then we like to use this activity for our purpose to challenge the green ammonia production using a green hydrogen and without any fossil fuels. So this is our latest challenge, big challenge. So we are not quite sure we will be successful or not. Anyway, now acknowledgement. I like to acknowledge especially to Professor Tamaru, my supervisor, and other staff members. They are my teacher who taught how to study the catalytic reactions. And here is the Tokyo Tech members. These are the staff members, and including the postdocs and students. And this is the University of Tokyo's staff members, and also we have a lot of postdocs and students. And at Shinshu University, Professor Hisatomi is my collaborator, and these are staff members. And then we also have a good number of students and postdocs. And this is a domestic collaborator, and maybe I forget some names. But of course, I have many number of international collaborators. Maybe due to my poor memory, I forgot some important names. In that case, I apologize that. And the funding is that from government is MEX is a Minister of Education and Culture, Sports, Science, and Technology. We obtained many different projects. We also obtained from METI. METI is a Minister of Economy, Trade, and Industry, considerably big funding. And fortunately, we also received many funding, many support from private companies. Here, I just show only 4 company names. Okay, anyway, thank you very much for your kind attention.